Hi, this is Bill Foote, and this is Stats 1, Lecture 9. And in this very first part, we went over some of the aspects of pose and form. Pose the question of now we're talking about revenue, and we really are getting into the business of correlation, which is more of a counting issue than anything else for us. I looked at a driver model. Did a little bit of the back of the envelope with a downward sloping demand curve. Then I abruptly stopped because I said, oh, let's do a correlation. Yeah, let's actually do a correlation. So here's the wire diagram for a correlation. We might have three prices. We can calculate an average price, and it behooves us this is what we're always going to be doing in statistics, is we're going to look at how individual pieces of data deviate from an average. So we're going to compute deviation. And we've done this before. And then we have a bunch of units sold. Call that U for the moment. Suppose we have 3 of those. And we calculate their means. And it behooves us, terrific word these days, compute the deviation of units sold from the mean. So having done that, our next job is to ask the question, is there a way to come up with a measure about if prices go up, what happens to units sold, and vice versa? And the measure is to take each of these deviations and multiply them. Now, what is the idea behind this? Some of these deviations may be greater than the mean. Some might be less than the mean. Now, if they're less than the mean, the deviation will be negative. If they're greater than the mean, they'll be positive. Same with price. So if we have a negative deviation from its mean of units sold and a positive deviation from its mean for price, some of those prices are high and units are low relative to their means. Relative, very, very important. Okay, let's pull this off here. It's very important. We multiply those together, we will get a negative number. Now, similarly, if you have positive and positive, you get a positive number. When you add up the negative, negative, and positive deviations, what do you get? Even in the Bronx, you may get a positive number or a negative number. We're going to be very simple here, and we'll be dividing this by n, the number. In this case, it's 3. And lo and behold, we have what is known as the covariance between, in this case, units and price. Now, if we carry this one step further, this number can go from a really big negative infinity to a big positive infinity, and anywhere is in between. So it's not very useful, and that's because it's dollars Lancasters. I mean, it's a meaningless dimension. And we don't do enough dimensional analysis, I believe, in any of the work that we have here. And I think it's something that a lot of us had to learn in physics when we were when we were hijacked into that course. We actually began to like it a little bit. It was pretty interesting, very tangible. But dimensional analysis is really useful here. So if units is just a number of cars sold and P is the price, well, it's price cars or dollar cars. I mean, which means nothing except maybe to the advertiser. So we want to create a metric that's a little bit easier to understand, and we do that. One way we do that is take the covariance and divide it by the standard deviation of price times the standard deviation of units. If you do that, you come up with a dimensionless number. Standard deviation of price is in dollars. Standard deviation of units is in whatever the units are. You know, gallons of shampoo. I mean, whatever it is. Covariance is similarly a product of the two. So one dimension divided by the other, the dimensions go away. And this number is what we call correlation. And it can range between -1, wander through 0, and be possibly a +1. A -1 is extremely uncorrelated. I'm sorry, extremely negatively correlated. And 0 has the notion of having no statistical relationship at all. It's just a great big cloud. It will look like this in a scatter plot. A great cloud of the unknowing from Bonaventure's consolation. Is it this way? Is it this way? Is it this way? Is it this way? We'll never know. There's not enough oomph there to find a correlation. This positive correlation, that's negative correlation. So some ideas there. Now let's immediately go to our spreadsheet environment, if I can find that thing, this glaring board I've got here. Created a new spreadsheet just for this purpose. Give ourselves a little bit of room here. So here's price. We're going to do price minus, I'll call it P bar. That's the bar over the P, which is the standard way of doing our averages or depicting our averages mathematically. So these are the objects of our affection right now. There we go, rediscovering everything here. There we go. Let's center these up so we can talk about them a little bit more easily. Well, suppose our price is $100, $200, $500 per $500 per unit. We can pretty easily compute the average of this as the sum divided by 3. So that should be the 9, 10, and 11. I mean, you could just as easily have used this. It's more typing in a sense. They have the same answer. Always check your formulas. Now we can compute the deviations. There's P bar. Sure, when you do something like this, you don't forget what I just did, which is make that a frozen object. So 100 is obviously below the mean, as will be 200. 500 we know will be above the mean by so many units. And suppose that at the same time, now this is important, at the same time you observe a $100 price, you observe a 2,000 unit sale. A $200 price, the price goes up, you only see a $1,000 or 1,000 unit sale. And at 500, you only see a 400 unit sale. Okay. It'll look a lot like our curve. And if we, again, copy and paste this over, that is the average units sold. Create the deviations. So I'm doing this for a couple of reasons. One is to simply use Excel as a calculator, really. Okay, so we have positive deviation here and negative down here. Now, just seeing this pattern right now, I know they're going to be negatively correlated to one another from the deviations. But you also obviously see that when the price goes up, the units go down. Deviations is what's going to matter to us. Okay. The next piece here, we multiply. I'm just going to do a deviation price times deviation in units, both from their respective means. So let's do this simple multiplication of that price deviation times that unit deviation. Pretty big number. And as I told you, these could be very large or very small positive or negative numbers for covariance. And we're going to sum these up as well. Don't want to have an average here, but we can sum them up and divide by 3 again. There we go. That number, that minus 102,000, is what is known as the covariance. All right. What are the standard deviations of our two erstwhile prices? Well, we can take deviation of price and square it. We can take the deviation of units and square that to get our variances. Take the square root of the variance, you get standard deviation. And you know where I'm going with this. I'm going to be computing the ratio of covariance, that great big negative 102,000 number, divided by the product of the two standard deviations. That's where I'm going with this. Let's go there. This is equal to that number squared. Notice it becomes positive. And the deviation of units sold squared. Okay, big numbers. And if we take these numbers and divide it by 3, sum them up, divide by 3, we have the variances. But again, dimensions matter. A variance is price squared. That's the dimension of the variance. And units, variance of the units is also, in this case, square units. Now, that would be great if it was length times width and my living room 14 by 7. Yeah, that would be fine. okay, or square footage of a commercial facility. Okay, yes, that needs to be squared. Absolutely. Area. These are not areas. In a sense, they are because they're squared. Yeah, I'll go with that. Okay, let's just pop this here. So we have one more operation to do, is to take this number and raise it to the 0.5 power. That's the square root. Same with the other number. So correlation will be this divided by the product of this standard deviation and this other standard deviation. Okay. Okay. First of all, there is an Excel function called covariance, or I'm just going to use Covar. That's been deprecated. And it's the covariance of this list of prices against this equally long list of units. Now, it's extremely important that these are pairs. I can't change it because I'm looking at relationship of one versus the other. So I have to preserve the pairing of 100 with, I'm sorry, that was incorrect there. Wait a second. Of 100 with 2,000, and of 200 with 1,000, and of 500 with 400. I have to preserve that pairing. If I do this, I get the same number. I just wanted to show you that there was a formula getting the same thing. Okay, and variance. Variance, there we go, VAR. It doesn't mean value at risk, all of you finance aesthetes. The variance of price. Okay, gives me this. That variance should have given me this number. So divided by 3. It doesn't. Why is that? Let's give me something close to this. And this is why we always check these formulas, make sure we're doing things correctly. It gives me that correct number for the variance. That var, I don't know what that var was, but var p. Again, I don't typically even use these formulas very often, but when I do check them. So I got that correct. Var dot p, and p of course stands for population. How do you know that? Because you looked it up. Don't assume anything because things change. That gives me, yes, it gives me exactly the correct one right there. Okay, so we just had some Excel formulas check our work against Excel getting checked against us. All right, but what we want really is something called correlation. This is only the beginning of the story of correlation, by the way. 2 R's and an L. That's, I think, what that says there. So you again need P and U. And we get minus 0.911. Now, that's very close to -1, which means extremely well correlated, but I think you can see that. Definitely can see that up here. Okay. Now, let's see if our formula works. Our formula is to take the covariance, this big number here, and divide it by the product of the two standard deviations. Okay, something horrible just happened there. Yes, divided by 0. So I need this number times this number. We're going to need to put those in parentheses so there's no confusion about the order of arithmetic operations. We get exactly the same number. I just wanted to show you that Excel is working as it should. We looked under the hood, came up with prices in units, deviations, and computed a whole bunch of things. But we have a what's the downward slope here? That's upward. There we go. Downward slope between P and Q, right? So that's the correlation, and we will be using that in our next round of work with our data model. And that's just a quick preview here. What we're going to be doing is taking our original model here and adding a price vector. A price vector is yet to come. Make sure that when we do that, we make price, regrettably it has an uppercase, but price, make that a named range. On that happy note, we will cut out again and resume again to a part 3. So see you on the other side of this video. Thanks very much for your kind attention.